Hello, everyone. Welcome to Pre-Lecture 6. This is going to be for our lecture on Thursday, January 27th. So where I want to start this pre-lecture is talking about measures of concentration. And that is because to end chapter 11, we're going to be talking about colligative properties of solutions. And so what is a colligative property? These are properties that are affected by the concentration of solute in a solution. Okay, so that's a general definition. However, before we get into those, I want to expand our understanding of different units of concentration, or how we might measure concentration in chemistry. And so one that you are all familiar with already from Gen Chem 1 is molarity. So molarity is, of course, the moles of our solute, and then we're dividing by the liters of solution. And so, of course, you know already that molarity is moles per liter, but we can add these kind of qualifying words to be a little bit more specific, to say that it's moles of solute per liters of solution, right? However, the potential issue with this is that when we do volume, so liters are a measure of volume, right? That is a property that is going to be temperature dependent. And so that means that the concentration in molarity may change across a range of temperatures because our volume is going to change. And so that's why that's part of the reason, at least, we'll use different measures of concentration when we're talking about these colligative properties, okay? So one of these other measures is a mole fraction that we designate. This looks like an X. It's actually the Greek symbol chi. And so the mole fraction of some compound A is going to be equal to the number of moles of our solute divided by the total number of moles of all of the components of our solution. Okay, and so that is our mole fraction. We also have molality, so that is designated by a lowercase m instead of an uppercase one. And molality is defined as the ratio, the number of moles of solute divided by the mass of the solvent in kilograms. And part of the reason I made this blue to kind of highlight this is because with molality, it is our only measure of concentration where our denominator is in talking about our solvent, not the total solution. Okay, so that is something key to remember, is that molality, we're talking about solvent instead of solution in our denominator. Okay. The next three are all very similar. So we have mass percent, parts per million, and parts per billion. These are all going to be fractions. So for mass percent, we start with the mass of the solute, divide by the mass of our solution, and then the percent. So if you break those apart, per, and then cent being century or 100. So we have a fraction multiplied by 100. That gets us our mass percent. Okay. Alternatively, we have parts per million. We start the same way. It's the mass of our solute divided by the mass of our solution, but instead of multiplying by 100, we multiply it by 10 to the 6th. And so if you remember, 10 to the 6th is equal to 1 million, thus parts per million. And of course, the same is true for parts per billion. We start the same way, but instead of multiplying by 100 or 10 to the 6th, we multiply by 10 to the 9th. Okay, and that is parts per billion. So getting into some of these colligative properties, the first one we'll talk about is vapor pressure depression. And so hopefully you remember what vapor pressure is. And if we have a liquid and dissolve a non-volatile substance, such as salt or sugar, in a volatile liquid, that is going to result in the lowering of the liquid's vapor pressure. And so why is this? We know that vapor pressure is when we have some amount of our substance as a gas, some amount as a liquid, and it's reached a dynamic equilibrium between the two, where we go between the liquid and a gas. So in order to vaporize molecules, they must be present at the surface of our liquid. And anytime we dissolve a non-volatile substance, represented by these blue spheres here, this could be, again, salt or sugar, anything that's non-volatile at that temperature, it essentially just takes up space at our surface. And so some of those molecules are going to block the surface of our liquid, and that is going to keep some of our volatile liquid molecules from turning into a gas, thus lowering or depressing the vapor pressure. Okay. The property of condensation, so our reverse process where we're going from a gas to a liquid, is going to be unaffected by the presence of solute. And so the net result is that our vaporization condensation equilibrium shifts so that it can be achieved with fewer solvent molecules in the vapor phase. And so that is why we have vapor pressure depression. Okay. We can quantify this in essentially our solution equivalent to Henry's law. So instead of Henry's law, we have Raoult's law. And it is shown here where we have the partial pressure, so the vapor pressure of any component being equal to the mole fraction of that component multiplied by the partial pressure of that. So that P sub A star, okay? So it's important, kind of a key thing that a lot of students forget is determining what kind of particle you have in solution. And so, for example, if you have an electrolyte like sodium chloride, when that dissolves, it's going to produce 2 moles of our solute instead of just 1. Compared to something like sugar, that's a covalent compound that won't dissolve into multiple particles, it'll be a 1-to-1 ratio. Whereas when we have sodium chloride, it's a 2-to-1. And so that would double our mole fraction, okay? Reasons we might care about this. This is an incredibly important process to things like refining oil. And so we can get these different kind of oil refinery columns. This is what they look like from the outside. And then based on how volatile something is, it will go higher and higher up, essentially. So the things that are most volatile essentially go out the top. Otherwise, next we have like gasoline, naphtha, kerosene, diesel, other fuel oil, and it all comes in as just kind of crude oil, and then it's eventually heated and separated by its boiling point, essentially, right? So there you go, an interesting application for how vapor pressure might be relevant for society. Okay. In addition to vapor pressure depression, we have boiling point elevation. And so this is when we lower the vapor pressure. When we do that, it also raises our solution's boiling point, okay? And we can quantify this using this equation here, where we have the change in our boiling point temperature, and that is going to be equal to some constant, K. It is the boiling point elevation constant. It'll be given to you if you ever need it. And then our unit of concentration here is going to be molality. So a reminder, that's our lowercase m, which is the moles of our solute divided by the kilograms of our solvent, okay? Great, so because this is a colligative property, this is something that is going to be affected by the total number of particles in solution. And so bolding that reminder there that it's not only the molality of what we start with, but if we have an electrolyte that is going to dissociate into multiple particles, which means that we have to take those into account for our total molality, okay? And we're going to, of course, do some practice with that in class, okay? In addition to boiling point elevation, we have freezing point depression. That is another colligative property, and it is the lowering of a solution's freezing point compared to the pure liquid, right? And so this will occur when we have some sort of solute present that is going to prevent or at least make more difficult the formation of the solid phase from the liquid, okay? We can qualify or quantify this using a very similar equation where our change in freezing point temperature is going to be equal to some constant, freezing point constant again, multiplied by the molality. Okay, so very similar to our boiling point elevation equation. And so if we think about this in terms of our phase diagram, what our colligative properties do for us is essentially keep things in the liquid phase longer, right? If we raise the boiling point, if we lower the freezing point, all of that is going to keep things being a liquid longer. And so this kind of shows with the dotted lines how our boiling point would change so that we stay liquid longer, and how our freezing point would depress so that we also stay liquid longer. And so those are the basics of a lot of the colligative properties that we're going to talk about. Okay. We'll talk about this more in class. If you have any questions, of course, feel free to let me know. Otherwise, I will see you in class. Take care.